No pasamos ningún problema.
Okay, this is for you, Miriam.
Let's do karaoke.
It's too big of a room. Okay, we're pretty relaxed on the time. If you want one to, so if you want to do one like this. Yeah.
Well, the Villafranca people go to lunch at once.
Okay. Well, in principle, I will control the time myself.
Yeah, you have
A clock, but I don't have glass.
you can
No,
have
nothing.
If you want me to, I can give you 5 minutes.
No, it's okay. Okay. The only thing, if I'm here like 1 hour and a half, just say, oh.
Step in if we get to, I'll step in if we get to sort of 5 minutes before 1.
No, obviously, no.
If Paco falls asleep, it doesn't mean you've been going for too long. Let's do it, yeah? Hi, thanks everybody for coming. I'm super happy to introduce Sergio. Sergio is kind of my academic brother. We finished the PhD at the same time at the Canary Islands in the Instituto de Astrofisica de Canarias. And ever since we've had parallel careers, I would say. So I could say many things about him, but I would like to highlight that he is one of the first ones who undertook observations and analysis of OB stars in the solar neighborhood in a systematic way. He has assembled this Jacob database you have up on top. If you want to know why this is called Jacob, you should ask him. He will tell you fun stories. And it's an amazing data set of very good spectra that he and his team analyze very carefully, and they are finding very interesting results on massive stars that I'm sure we will hear about today. And career-wise, he just promoted to Investigador Científico at the IAC, and he's involved in his own and also very big surveys like WIF and Foremost and Song, photometry, you name it. So I will not extend further from here. Thanks very much for coming, and I hope you enjoyed the talk.
Thank you very much, Miriam, for this nice introduction. It's a real pleasure to have you introducing me for the talk. I have to say that if I remember correctly, after 24 years of career, it's the first time I give a seminar in Madrid. And I'm from Madrid. So if other people from here, from the university or other places want to have me here, I'm happy to come to visit everybody here. Okay, I'm going to start with something that is really important but very basic, because I've been saying that not necessarily everybody here at CAP is astrophysicist and obviously not doing stellar astrophysics. So I thought that I wanted to start with something that I think everybody consider one of the most important milestones of observational stellar astrophysics. And this was more than 1 century ago. This slide is gathering 2 important results that I put here, some images of people, some names, but obviously I'm sure that there was many more people working on this. The first thing is what has been called later the Hertzsprung-Russell diagram. So it's a compilation of properties, observational properties from stars, what could be done by that time. So basically here in the y-axis, you have the absolute visual magnitude. So it's how bright is the star, putting all the stars at the same distance. So it's in some sense how energetic is this star. And then in the x-axis, I was using something that was called by that time spectral class, and we are still using that. And then other people in other group were taking a spectra and realizing that depending on the star, not only the stars had different colors, but also the spectra were different. And you could see this in different lines that were appearing in the spectra. So this is what they call the OBAFGKMN type stars. And then they realized that when you put the stars from one cluster, if I remember correctly, this is the Hyades cluster, then most of the stars were located in this diagonal band that was called main sequence. And then there were a bit other stars populating the diagram. So this was a very important milestone, as you will see along this talk, and has been a cornerstone to investigate stellar evolution, because has been kind of guiding us in many of the developments of stellar astrophysics. More than one century later, this is what we have in terms of HR diagram. And this is thanks to Gaia, that has been another of the milestones in stellar astrophysics. So this goes after other missions, like, for example, Hipparcos. And the idea is to go to space and use this basic idea of the parallax. So it's when you have the foreground and you put your finger, you see how, depending on if you open one eye or the other, your finger is moving. So this satellite, this mission is using the same principle to measure the distance to the stars. Distance is probably one of the most difficult things we have to measure in astrophysics. And having distances is very important, because only with distances we can really characterize, for example, in this case, stars with things like luminosities, masses, or other things. So basically, this mission have been providing parallaxes for almost 2 billion stars. Most of them are in the Milky Way, but also in other close by galaxies. And also high precision photometry. So now we can go, instead of these spectral types and absolute magnitude, we can go to a more reliable and homogeneous magnitude in the y-axis, and then colors, because depending on the temperature of the star, then you have that the spectral energy distribution is different, and you have a different color. That means that the difference between two colors or two emission in different bands is different. So now you have here the what we have in terms of HR diagram, and I'm indicating there the OB stars. That is what I will be talking about. During this century, we also had some theoretical developments, and we have understood that this HR diagram all is about masses, stellar masses, and evolution. So thanks to the development of the theory of stellar interiors and many people working on it, we have understood that the main sequence is a band where the stars are burning hydrogen in their cores. And then the diagonal is just a question of the masses, with the lower masses at the bottom and the upper masses in the upper part. We have also learned that the time a star spends on the main sequence is larger for lower masses. So this means that the massive stars that are at the upper part are evolving very fast. We have also learned that depending on if the burning is happening in the core or not, the evolution is faster or not. And also, we have learned that different masses evolve, or stars with different masses evolve in a different way and end their lives in a different way. And basically, this has led to a division of the diagram into regions. One is the intermediate and low mass stars, and then the massive stars. And basically, it's more complex, but just generally speaking, the lower intermediate and lower mass stars are not massive enough to allow to burn elements farther than helium in the core. So then the star ends as AGB, and then after the planetary nebula, where it's spelling all the outer layers, you have a stellar core. You have the white dwarf. But then when you have more mass, at some point you can go beyond helium. You go burning carbon, oxygen, and other elements until iron, where you cannot burn anymore, and then the stars, in a process that probably you've heard, and as a core collapse supernova, the core is collapsing, and then you have this a very energetic explosion, and leading to neutron stars and black holes. And this is happening more or less at 8 solar masses. Now, the other important thing I wanted to highlight here, just for people to know the importance of what we are doing in terms of observation, is this other finding that Salpeter found, that it seems that the formation of stars tend to go more or favor more the lower mass stars. So the number of high mass stars is much lower than the lower mass stars. So for example, here I show how the 30 to 60, when you have one for each one of these stars, you have 100 stars like the star that are formed. So this means that every star, high mass star that we have is a real treasure for us because there are not so many. So it's not like when you go to study low mass star that you have so many that you can do many things in terms of interpreting observation or compiling data. Now, this is photometry only, but we have spectroscopy, as I said, and beyond the first photographic plates where they could realize that the spectra were different depending on the stars, there have been many good developments in terms of instrumentation from the technical point of view of the telescope and also the instrument, the spectrographs. And now we can gather, or we have been gathering very high quality data, spectra for many, many, many stars. So for example, here you see, again, in terms of spectral types from the chapter of the Encyclopedia of Astrophysics, how the stars are different, the spectrum is different depending of the OB and then the other stars. So it's clear that we can, with the spectra, we can really identify the stars and select them and study them depending on how their spectra look like. But not only that, we've been able, thanks to the development of theory of radiative transfer and stellar atmosphere code, we have been able to extract from this spectra that is just the photons emitted by the outer layers of the stars. We have been able to obtain information about the stars themselves beyond these magnitudes and colors. For example, rotational velocity, effective temperature, surface gravity, surface abundances, and also the properties of the wind. So for example, here you see an illustration of how good we are now in fitting spectra. This is a B-type stars using the stellar atmosphere codes that we have. This is a B0, so it's an example of one of the stars that I'm studying. But the same is happening for the other stars also. So this is very good because we are in a moment in which the tools to study stars are in a very good shape. In terms of interiors, stellar evolution, in terms of atmosphere and wind, stellar atmospheres, and then in terms of how we model them. This is again an example. For example, for a O-type stars, you have different diagnostic lines, Balmer lines, hydrogen lines, helium-1, 2, and H-alpha, and then you see these parameters, temperature, gravity, and the strength of the wind. Depending on how you select it, you have the red that here is not fitting, but then by fitting the lines that you obtain the parameters that you want to obtain. So it's very, now we can characterize the spectra, the spectra of the stars via their spectra. And this has allowed to go to, from my point of view, another milestone now in terms of massive star astrophysics, because it's an example, a result compiled by our other colleague, Norberto Castro, who also did the thesis at the ISC. Basically, by that time, what he did was he didn't have still Gaia, and was using this, what is called spectroscopic luminosity, that is a combination of the temperature and gravity, so parameters that you can obtain from the spectra. And then he went to the literature, compiled all the stars, massive stars in the galaxy, from where you have reliable parameters or obtained parameters, not necessarily reliable. And then you see here something that is, you remember I was telling that depending on the phase of the evolution of the stars were evolving faster or slower, depending if this burning was happening in the core. So this means that when a star is evolving slower, we are able to observe more of this star. When a star is evolving faster, there will be more difficult to observe one of these stars. So if you compile a lot of data, then depending on the density of the stars in this diagram, you will see, you can connect this with evolution. No? So this panel or this slide here is very interesting because I'm connecting three different things. One is the density plot, is the number of stars that we have, and we see clearly where they are located. But also I put the evolutionary tracks from one of the models or the groups that are obtaining and modeling this evolution. And you see that, for example, here, the dots are the steps in age. So where you have a lot of steps, this means that the star is evolving not as fast as when it's jumping to another place. So you see that this is the main sequence, and this is the red supergiant phase where you are burning helium. And then you see things like, for example, observationally, this is not necessarily fitting. The end of the main sequence is not necessarily fitting with the observation. So this is telling us that we need to fine-tune our models. And then from the spectroscopy point of view, because first, before doing the analysis, that is a really heavy task, you need to characterize the stars. So then we have different types of stars, the O stars, the B supergiants, the early B dwarfs and giants, then the red supergiants, and then some phases, intermediate phases, where you have the yellow supergiants, the supergiants. So basically, this is in terms of observational properties, different type of spectra, also the world right here. So basically, you connect phenomenology, physics, and models. And this is a very good way to go to learn about what is happening in the evolution of the stars and also how the properties are. Okay. So then these are the OB stars, and this is the group of stars that I decide to concentrate on, as Miriam was suggesting. And why these stars? First, because it's, that's by chance I ended up in this project, but also is because, as I say, the most of the time the stars are evolving this is in the main sequence. So this is a very important, is the starting point of the evolution of the star. So we need to make sure that this is very well established, the evolution there and the properties we know very well, because if not, whatever we are kind of predicting in terms of further evolution, including the supernova, the number of supernova events, how the stars end up in terms of black holes and neutron stars, will be completely unconstrained, no? So this is the left part of the diagram where you have the hotter stars, and these are the properties. I can summarize this, and this telling you that these are very extreme properties in terms of stellar evolution, meaning or stellar properties, meaning that the modeling of the stellar atmospheres is very, very difficult. But many people in the last 20, 30 years have been working hard, and now we have models, and they are working very nicely to obtain parameters from the spectra. And the other thing I want to say is that these are very hot, so they have a very strong ionizing radiation. And in terms of OB stars, just two, because not everybody is using this term OB star in the same way. These are the stars that I consider to be O stars. So basically, from a mass evolutionary point of view, are stars in the early phases of evolution from having masses above 9 solar masses. Okay, I decided to include this because not everybody is maybe understanding everything I'm saying, so it's also good to give some interesting facts here. So I'm sure everybody here recognizes the Orion constellation here. And I'm not sure how many people know that many of these bright stars are actually massive stars, and they are kind of they are not physically related because they are at different distances, but they are covering different stages of evolution of the massive star domain and different masses. So you see all these, how they are distributed in the HR diagram. So I'm sure you know about Betelgeuse and also Rigel, and then all these stars, the other stars are here. So now, every time in late summer until February, March, whenever you see Orion on the skies, remember that you are basically seeing that stars that at some point will explode as supernova. And one of them can be Betelgeuse or Rigel. Also, we've been not only with models, but we've seen the humankind have seen stellar evolution. So, for example, there was a report by a Chinese astronomer 100 years before our era, saying that Betelgeuse, that now you know is a red star, was yellowish. So yellowish means that in terms of the evolution, it was traveling to the red supergiant phase. So this is also very interesting because, well, obviously there can be some bias in the way you make colors, but if we rely on that, this means that Betelgeuse is evolving to the red supergiant phase, not necessarily from the red supergiant, something that is interesting. Then we have the Clark Nebula that later was identified with a supernova, and it was identified that was a pulsar there that is a neutron star that is spinning faster. So this means that this was a core collapse supernova, and this was observed by, again, the Chinese astronomer, and we have an example of this core collapse supernova. And also, even close to when we are now, we have seen other supernova that we can study, and we were there even taking measurements. So this is something that is fascinating. I say that massive stars are scarce, but they are very important. They are evolving very fast. So whenever you see a massive star, mean that this is a star-forming region, because the star won't be there if they are evolving. So this means that star formation is happening. They have very strong stellar winds. They have ionizing radiation. They are affecting the interstellar medium, and they are also driving chemical and dynamical evolution of galaxies, because these stars are producing elements, generating elements and their cores. And obviously, this is a very nice example of how massive stars are important for the development of life as we know it here at Earth, no? Because, for example, oxygen, phosphorus, and many other elements that are relevant for life as we are generated by massive stars. But also, they were responsible of the reionization of the universe. So they were there at the very beginning of the universe. The very massive stars were at the very beginning, and how the galaxies have formed, how the universe has evolved, was they were playing a very important role. They are also extragalactic tools. They are very luminous, so we can obtain spectra in galaxies very far away, where you cannot observe low mass stars. So by obtaining information about, for example, stellar abundances, you can know what is the chemical composition of present-day material in these galaxies. So it's a way to expand our knowledge of the universe. They are connected with world riots, supernova, GRBs, pulsars, and even black holes, neutron stars, and even they are connected with something that now we are all fascinated, these gravitational wave emitters. So we now have a new way to study the universe, and this is just the merging of neutron stars and black holes, among other possibilities. So it's very important to study and understand massive stars for many aspects of the universe, and has very critical impact in many other studies of modern astrophysics. Let's go back. Massive star evolution. This is the basic, what probably everybody knows. Let's try to reconstruct the puzzle of massive star evolution. Star with a given mass evolve as a blue supergiant, red supergiant, explode a supernova, and then depending on the mass, you have a black hole or a neutron star. Good, but not necessarily so simple. So when you go to your master studies, and then if you continue in doing a PhD, and from there, you understand that things are a bit more difficult and a bit more complex. So it's not only mass that is affecting the evolution and the fate, it's also the internal structure, and the internal structure that is driving the evolution is complex. So you have convective regions, radiative regions, how the energy is transported from the interior to the surface. You have different time scales of evolution. You have things like core overshooting. Then stellar rotation is very important, because normally you have, the massive stars have a convective core and then radiative layers. This means that the material in principle shouldn't be able to go from the core to the surface, but we observe material that has been generated in the core, in the surface. How can this happen? Then we realize that the stellar rotation is kind of generating meridional currents that is mixing the material. But it's not only that the material is going to the surface and we can see it, it's that also the hydrogen, the fuel, is going to the core. So this means that you are affecting how the star is evolving, because the evolution is a question of burning products in stars. So how this is happening, the transport of material, how magnetic fields are affecting the evolution, and also if mass is important, since this star developed very important stellar winds, if the mass is going out due to the winds and also the angular momentum, you are modifying the stellar rotation and the mass. So then the evolution of the star depends very much on these two parameters. So for example, I was saying that models are fitting, not fitting. This is just an example again of how different models from two different groups and considering different rotation are modifying the tracks that are the lines in colors. So you see how things are different. So now we need to play a bit, and observations are really important, because at the end, any model has to fit the observation. So then it's like people is now, or we are trying to move the parameters of our models and understand the physics of our models to fit the observations, if we trust in the observation that we have. That is the other thing that is important. This is, for example, also what happened with a track for a given mass when it's not rotating and with increasing rotational velocity. You see how the tracks are kind of modified, and also the overshooting parameter. This is very important because one of the ways we have to derive the mass of a star is to put the star in a HR diagram, rely on a given stellar evolution code, and say, if the star is here, this is the mass of the star. But then if now you have so many tracks going around, it's like, what is the mass of the star? And it's very important for some studies to know what is the initial mass of the star. This is another example how when you consider different type of magnetic fields in the interior of a star, how the track is moving and is really varying a lot. And also the amount of elements that are reaching the surface is different. What is good? Because then we have abundances, we can test if this model or the other is correct. This is not enough because all this is when the stars are evolving as single. But we have learned something that is very, very relevant, that the percentage of stars in binary systems is really high. And then the evolution of the star are going to be affected because these stars sometimes are interacting. So for example, we have this fact that 70% of all massive stars will exchange mass at some point of their lives. When the mass is transferred, also the angular momentum is transferred. So you can imagine how the evolution of the two stars that are varying in their masses and spin will vary. This is, for example, a case here, how two stars, depending on when the mass transfer is occurring, how suddenly they can go anywhere. So then if you have one of these stars and you try to derive mass without knowing the track, you don't know what you are happening. If you are trying to use a star that you thought that was single, but it's not, the conclusions you are extracting are not correct. And this is just to show also this part here to show how this happens. How the spinning of the stars vary when you have this binary interaction. I will come back to this soon. Also, observationally, this is making things more complex, but also more funny. When you have two stars of similar mass, they will be detected as virtuous system. You will see two lines moving. But then if one of them, the more massive, is evolving, at some point you will see a very bright, luminous red supergiant with a very small blue star. So this is going to be dominated by a red supergiant. You have the companion, but it's not so easy to identify. At some point, this red supergiant can explode a supernova, and then in some occasions, you will have a black hole with a blue star. So you have a SB1 system that you don't know, if you obtain only one spectrum, you don't know that it's a binary. So you are interpreting a star as single, while maybe there was some mass transfer. Sometimes we see the black holes because we have the disk and the X-ray emission happening. And then this is just to continue with the image that this person generated. This is just to say that at some point you will have two neutron stars or black holes. And then if they merge, you will have the gravitational wave event. But also when you have the supernova, it can happen that the blue star the binary is disrupted. So then suddenly you see a star that is single. Even if you have multi-epoch, you don't identify it as single, but it's a fast rotating runaway, so the star is escaping. So you also need to know if the star is moving, not only in radial velocity, but also if it's a runaway. Or sometimes you have that after the mass transfer, the other star, the strip star that we call it, is very faint and hot, while you have the other, the gainer, that has varied completely the properties due to the mass transfer, but you don't see the donor. So it's very important, all this to say that it's very important in terms of observations to know what you are observing and interpreting correctly what you have. So all this ends up in a situation that we are in a shaky moment. We have the tools, but we are not sure about how things really go. We know that we have single stars, binaries, rotation, mass of rate, but then we need constraints for that. So one of the ways to do it is to construct this or to compare all this with the observations. As I say that the number of massive stars is much more smaller. So whenever you go to the normal surveys, they will be dominated by low mass stars. So it's very important that we, the massive star community, are also there, ensuring that the massive stars are also observed. Because even they are very low, very, very small in numerals, they are very important. So we need to compile this observation. And this is what is happening now. This is an example of what is happening in the galaxy, but other efforts are also done in close by galaxies. So we have the big surveys. One of them is Jacob, that I will tell you about. We've reached about 3,000 stars, high resolution, multi-epoch. This is a 15 years project already. But now, very soon, we'll start two very important surveys that is foremost in the southern hemisphere, and then in the northern hemisphere, where we are increasing by 1 order of magnitude the number of stars, of massive stars, that we will have good spectra to do the analysis. And you will see why this is really relevant. So about Jacob, this is what I started in 2008, and the idea was to benefit from the telescope, middle-sized telescope we have in the Canary Islands, to observe bright stars. So we can do also science with a small telescope. It's very important to keep them and maintain them, because even they are bright stars, there are, as you will see, important things to do with them. So the idea is to not go to specific small samples to give results that maybe are spurious, but to do a holistic approach, observational approach to the problem, and observe as many stars as possible. Initially with this telescope, and now with WIF and foremost, this will explode. And then do everything together in a coherent, in a comprehensive way. Observations, determination of parameters, abundances, identify if these are binary or multiple systems. Also, study stellar variability, because the stars are variable due to other things, and make constraint for stellar evolution and stellar atmospheres. So this is the outcome after this year. I say that I will stop observing. So now my students are continuing this, but I'm not, I'm wrapping up the project as it is now. It doesn't mean that the science will not continue. So we've reached almost 3,000 stars. And you see what is the coverage in terms of mass from 9 to 60, 80. And then you see also the x-axis is evolution. And we divide this in these 3 regions just from methodological reason. These are the kind of spectra, so very good spectra. All these are available if you want to have a look or to use them for anything. And these are all the things that we're obtaining. It's also multi-epoch, and we go to time series. Because when you go to multi-epoch, you begin to identify binaries and also variability of things. I'm not going to enter today in these things, but just for you to know. But we also need UV spectroscopy, because as probably both Miriam and Paco has told you many times here, UV spectra are very important to characterize the stellar winds, also the infrared, but UV is critical. And then, as I say, for the fundamental parameters and other things, you need Gaia. And then TESS is another mission I won't talk about today, but it's giving light curves for many, many stars in the sky with high precision. And this is allowing us to study variability and detect eclipsing binaries and other variables. So now this is an example of what is happening. So in 2015, we have this spectroscopic HR diagram with these were the number of stars that we had at that time. And then thanks to Jacob, excluding the SB2s, this is what we have now. So we are increasing the coverage of the region we are interested. And since we have multi-epoch, we can also separate the stars between presumably single, because you never know if at some point, if you observe more spectra of the star, maybe you see that it's a binary, but also the SB1 and the SB2s. So for example, this SB1 could have a low mass companion, could have a black hole, a neutron star, and the SB2s are stars that are in a similar evolutionary phases. So this is the kind of things that we can do, and not also in the O-star domain. That is what I'm including here, but also extending in terms of evolution and also in terms of mass. So we want to do all this in a comprehensive manner. And this is the people that have been mostly participating. I have many other collaborators, but I wanted to put these faces here. You will see the names at the very end. And also, not necessarily for us, but also interesting for other studies in terms of covering or surveying the galaxy. This is where the stars are located. So you see that we are reaching good distances. So this can be also used for other studies. And also we can go to volume limited samples, not magnitude limited samples, because the supergiants are brighter than the dwarfs. So whenever you have density plots, you are going to have more supergiants if you don't select them in terms of volume. If you select them in terms of magnitude, so then your ratios of density of stars in different regions will be different. So I want to mention a few highlights selected given the time that I have and that I wanted to give this introduction, more general introduction. And then one of them was obtained by Gonzalo Holgado, who was the first PhD student of the Jacob, and he was concentrated in the O-star sample. And from a sample of 500 stars, more or less, he's selected those that were not identified as SB2. And this is the diagram that he created, but that time Gaia was still not providing the parallaxes that we needed when he finished, was about, but not yet. So we were using this spectroscopic HR diagram instead. And this is something that people had been mentioning for a while, but we were kind of also reinforcing this result that it seems that we don't get to observe stars that are close to the SAMs. The SAMs is the zero-main sequences where the stars are starting burning hydrogen. And this should be there. So what is happening there? Some people say, oh, maybe it's because they are extinguished, they are still embedded in the cocoon while they are accreting. They evolve very fast. So we did our best. We evaluated many things, but these stars are still not there. So this is an open problem. There's a very kind of interesting discussion in the community, because not necessarily can be an observational problem, okay? But I also like to, when I saw the result by Lionel Hammerle, I found it interesting, because maybe what is happening is that the way the massive stars are evolving, or the connection between formation, that is, start accreting mass until they start burning hydrogen, and evolution, in the massive star domain, maybe these things are mixed, because maybe the mass that the star is accreting is so large that the burning of hydrogen is happening before the star is stopping the accretion. So maybe if you modify your accretion rate, that is something that in the models, this is a free parameter that you're fitting. So for example, if you consider that these stars, you have to reach these stars, then you give your accretion rate during the star formation to say, okay, you have to reach this star. But if these stars maybe are just binary products, and they are evolving in this direction due to the way stars evolve when they interact, and imagine that this is what is called in the low mass star domain the birth line. That is when you observe the star. So maybe what is happening is that the star is evolving, burning hydrogen while also accreting. So then the star is accreting mass, but already evolving. So maybe this is the reason why we don't observe this star. Not necessarily, but I think it's good to be open to possibilities in science, in astrophysics, because maybe this is the explanation for that. Then in terms of the TAMS, that is the terminal main sequence, once the stars finish burning hydrogen, they are jumping to the red supergiant. Well, this is a basic statement. It's a bit more difficult, but basically, once you have hydrogen burning finishing, main sequence finished, and they go to the red supergiant. So then, in terms of, as I was saying, the density of a star will depend on the time spent by the stars in this phase. So then, as soon as you have the end of the main sequence, stars should be traveling. So you shouldn't observe so many stars, and this is something that in many studies was shown, and also Castro's plot were showing that. But the problem there is that it was a compilation from the literature. So it was probably affected by observational biases, because there were many more blue supergiants that are the stars that are located in this region, because they were brighter, and people were using them to do other analysis. So you go to brighter to have good spectra. But now we can restrict our samples in volume. So now it's more reliable. We don't go to stars that are farther away. And then we begin to see a clear drop in the density of stars here. So this is what we are proposing as a reliable terminal main sequence, that now we can give it from 9 solar masses to 80. So this is very, very important for constraining models. This is only with 600 stars. Now still you see that you begin, this is from 1.5 kiloparsec to 2.5, 200 stars, 600. You see how things are improving, but still, I want more. So this will come soon with for most, but because imagine that instead of 600, we have here like 15,000. So then things will be stronger in terms of observations. And also we see how I told you that we were detecting binaries. So there is also a clear drop in the relative number of binaries beyond the main sequence. This is also very important to understand binary evolution and see how the binaries can go in a region that is forbidden in terms of single star evolution. Okay, rotation. This is a usual distribution that we have in massive stars. Normally, probably you've heard that massive stars can reach very high rotational velocities. Sure, up to 500 kilometers per second. Can you imagine that? But this is a tail of only 20-25% of the stars. So when people observed these distributions a long time ago, one of the first studies was in 77, when I was about to born. And they were saying, okay, what is causing this distribution? Because this is, in some sense, there are two things. One is how the angular momentum from the cloud, the formation cloud, is distributed in the stars, but also how the stars evolve. Because if you have winds, then the surface is spinning down. So then you need to understand all these things. And by that time, they had some ideas, some speculation, but they didn't have a proper understanding of winds and everything. So some people were saying maybe what is happening is that the massive stars, since they are not developing important magnetic fields, they are not spin down, as in the case of the sun or the low mass star. So then they are born with very fast rotation. But then why you have this here? It's a question. The winds are just moving out all the angular momentum, and then the stars are spinning down. This was one possibility, and this is something that we can do. But then you have different models. This is two different families of models with different physical assumptions in the interior. And you see here that this is rotational velocity versus temperature, that is kind of time in evolution. And then you see that one possibility is that the stars, due to the winds, are spinning down. But then the other is that it's not. So depending on how you consider the transfer of angular momentum from the interior to the surface, you will have this surface breaking or not. And also you have this thing that when you transfer mass, you also transfer angular momentum. So then the stars, the gainer, is spinning up. So then to understand this, you need to go a bit farther. And this is a result obtained by Gonzalo. And as you see how when we separate, we have a statistic enough to separate the stars into regions here and here. And then you see that this main peak is in the same position. But this is the region where winds are important. So this means that the breaking is not happening. So either the winds are not so important, or the angular momentum transport from the core to the surface is very efficient, and then is kind of maintaining the surface properties. This is what we think is happening. And then we have that this tail of fast rotator is just the impact of binarity. Okay, this is also happening when Abel de Burgos, who was the second PhD student of the YARC project, extended to the B supergiant. You see here how this main peak is so if the surface breaking would be very efficient due to winds, all these stars should be almost zero, and this is not happening. So we think that this is because the internal angular momentum transport is very efficient to the surface. Okay, this is about the possibility of detecting or testing this hypothesis that the fast rotating tail is due to binary interaction. So in this case, when you have the binary, the gainer, that is what you see, then you expect to see less SB2, because then the donor has given a lot of mass and you don't see it anymore, or maybe there's a black hole, a neutron star, or maybe this has exploded and then the binary is disrupted, and then you have a runaway. And this is something that we have begun to understand. The number of stars is still small. We want more spectra, and this is what WIF and Formos will give us. But it seems that the percentage of runaways is larger in the tail. The percentage of SB2 is smaller. So it's going in this direction. So I cannot enter into many details, but it's just to show you how observations and big samples are helping us to understand what is happening. And this is the last one. just sometimes we have serendipitous, we find serendipitous, obtain serendipitous results that is like, even this is not fitted. So the CNO cycle that is happening in the core is very well known. And when you have transport mechanism, then you should see in the surface, whatever is happening should be mimicking what is happening in the core, if it's going in this direction. And then we found that different models with different physical assumptions, all of them were traveling in this kind of track in the nitrogen over helium diagram. So you have hydrogen that goes into helium with the CNO cycle that is increasing nitrogen during the process, to say it in a few words. So then you see that when you increase helium, you also increase nitrogen, and the way you increase it is in this along this track. This is broad because it's including many different possible models and assumptions and blah blah blah. Then we are observing stars that are rich in helium, poor in nitrogen. This cannot happen if the transfer of the material is going from the core to the surface. So then the other option we have, either we are not obtaining proper abundances, could be, always. I'm very critical with the work I do myself. But maybe what is happening is that you have transfer of mass from the gainer. So then things are different because not necessarily is the well-behaved CNO cycle transferring products transferring to the surface. Then when you have the mass transfer, depending on how this is happening, then you can have this situation. And now we are working with the Bond group, and they obtain this with binary models. So it seems that we could be supporting this. I'm going to stop here. I don't know how long I've been, so 15 minutes. So I think this is more than enough. But there are many, many things. It's just we have this puzzle. We have a lot of pieces. We'll have more. We have the ideas, but not necessarily we have the image guiding us, because the image is our theory, and maybe we are just in another box, and we are trying to fit pieces of the puzzle that the image is in the other box. So we need to be open also to other boxes. And these are the main takeaway messages, that basically is thanks to these spectroscopic surveys, we are now in a golden era, and to understand the properties and evolution of high mass stars. Things are a bit more complex than we imagine. We thought by the beginning of this cycle that things were more or less okay, but as we are comparing with observation, we are finding more and more things that are not necessarily fitting properly. There are other things that we are doing that are fitting. It's not that everything is bad, but yeah, and thanks to the larger and larger massive star community, and the observation that we'll have together with Gaia and TESS and many other observational facilities, then nice times are coming for the massive star research. Thank you very much.
Thank you very much, Sergio, for that fantastic talk. I particularly like the side about the red supergiants. I'd sort of forgotten that this result about Betelgeuse. So that was really interesting for me.
Yeah.
So let's kind of open the floor for questions in the room here first, and then we can go to Zoom.
If you don't ask a question, I will ask a question for you. Okay.
I've got one question related to these nitrogen poor helium rich stars. Do you get a hint from their rotational velocities whether they are all those fast rotators?
Yeah, so this result that was obtained by Carlos Martinez Sebastián was when he started obtaining abundances in the old type stars, and he was learning, and he started with the low BCNI stars because they are the easy ones. So this figure is only for stars with BCNIs below 150.
So do the binary evolution calculations by the Bond group also? I mean, one thing is the abundances, the other is the rotational rates. So are they also slow rotators?
We are kind of working on it, but something that I learned in the last months or last year, where I started to go into the binary business and try to understand, is that there are things in the models that are kind of good enough as a starting point, but not necessarily. There are many approaches in the way they are doing things, if I understand correctly. Obviously, we have the first set of population synthesis models, but now this is, not necessarily the mass transfer process is quite a tricky thing, but also depending on how the transport of angular momentum is happening in the star itself. So if you have, if you are transferring mass and angular momentum, but then depending on if you have an efficient transport of angular momentum from the core to the surface or not, you are going to distribute things in the other star or not. So it's the combination also between this and that. So I think many of those should be in the models fast rotators, but not completely sure because I haven't gone through so we are now going in this direction to see what's happening. But this is even more critical because it's low VCNI and rich helium. So not even with the single stars, it's even worse for the single star. Yeah, but we are going in this direction.
I will use my my microphone. So Sergio, in the I think it was Gonzalo's studies of the rotational velocity that you found that this one and the possible explaining hypothesis was that the angular momentum is being transferred very efficiently from the core to the surface. Have you considered the possibility that maybe the stars are younger than you thought, or that the winds have started to expel matter after some years after the suns, or things like that? Some other possibilities.
Yeah, one possibility is and this is something that there have been some development that the winds are not so strong. So the winds that are considered in the models are not so strong, and this is related to wind clamping and all this could be. But when you are here in this domain, it's like, okay, could be this, but then you go to the continuation of the work with Abel, and even in the stars that are beyond the main sequence. So this is where winds should play an important role. So we see this happening with evolution. And then on the other hand, why these stars that are here at the very end of the main sequence, why you still have the fast rotating tail? Obviously, it's something that we keep our eyes always open, but I find it more natural the other. But in terms of young stars, they are very far away already from the sun. So
I thought you were going to take it to mergers and things like that. But
no, also, I mean, yeah. Then again, we have the same mergers. Some people say that they should be fast rotators, or depending if you have a magnetic field, should be low VCNI stars. But all this is model dependent. So yeah. So this is why I'm kind of, now that I have all these results, and I thought that already we were going to provide definitive answers, we see that we need more statistics, and we need the characterization of all this, because at the end, if not, with models, some way you can do whatever you want. Then you need to. So this is why, for example, we started to say, if they are mergers, there cannot be SV1s. Well, always it can be triples. But I mean, if you see SV1 in this region, it's more unlikely that it's a merger. But obviously, that's the point. There are so many pieces to play with that.
and something very interesting about all the work you are doing, all the team is doing, is that you follow these things at different stages of the stars, which means that you can follow what happens in the younger population to what happens in the older population and do this kind of consistency checks.
Or for example, the other things connected to this, is now we can go back and see how these properties, these outliers from what are the properties of this with respect to the other. So maybe connecting all these pieces, we begin to see, look, that these are this, are this. But it's only now that we have enough statistics to begin to see or to be able to have a more clear idea of these pieces and put them together.
Very much. Are there any more questions in the room? And I'll give just a little bit of time for anyone on Zoom to sort of be brave enough to ask a question, because they can unmute themselves and ask it directly. They can sort of raise a hand, virtual hand. We can let it out. But if not, then let's thank Sergio again for a fantastic seminar.
Thank you.